Okay, we're finally ready to look at the longitudinal dynamics of an aircraft. So just as a review real quick, we developed these equations here. This top set of equations here are linearized longitudinal equations of motion. Okay, and we developed those in the previous video, so hopefully you understand where this set of equations comes from. Now, notice that basically we can rearrange this equation. This shows us, this is our change in these 6 state variables, these longitudinal state variables. If we know the current value of those state variables and then some control deflection input, but if we know the current state of the variables, and we can predict from this equation here the change in that state of or those variable states. Okay, and so these are 6 linearized equations that represent our longitudinal dynamics. Now we're going to look at the homogeneous form of these, which means that we're going to neglect the control input. Okay, so we're going to look at the dynamics of an aircraft independent of the pilot. So this is if the aircraft were just allowed to respond on its own rather than having the pilot take any corrective action during this dynamic motion. And these equations have been linearized about some equilibrium state. So we have some lift coefficient that the aircraft is at, and we have these small derivatives or these changes in our forces and moments. We've linearized these about this particular state of the aircraft. Okay, and so these equations now are actually in a perfect form to plug directly into an eigenproblem. Okay, so these second set of equations, this is our eigenproblem. So these are our equations that say A minus lambda times B times this chi vector, which is our eigenvalue vector, eigenvector, is equal to 0. Okay, and so this matrix right here, this is our A matrix, so we just plug it in right there, and then this matrix right here becomes our B matrix, and now we just plug that directly into this eigenproblem. We plug that into an eigensolver, and out come a series of eigenvalues and eigenvectors. So from this 6x6 system, we're going to get 6 eigenvalues, and each of those eigenvalues are going to have 6 components of an eigenvector associated with it. So when those come out, one of the first things we want to do is to re-dimensionalize the eigenvalue information. So this is a non-dimensional system of equations, and so I'm just going to put some notes here. So for example, the damping rate, usually that's minus the real part of lambda that comes out, but because we're looking at this non-dimensional system for these longitudinal equations, when we re-dimensionalize that to get this in dimensional form, we're going to need to multiply that by 2 v naught over c bar w. Okay, so that's what we use to non-dimensionalize. And then omega d, so our damped natural frequency, usually that is the absolute value of the imaginary part of lambda that comes out. And again, we're going to need to multiply that by 2 v naught over c bar w to get that in a dimensional form. And then finally, if we had an undamped natural frequency, if we wanted to figure out what that is, omega n, then that would be equal to the square root of lambda 1 times lambda 2. Of course, these lambdas are going to come out in pairs, so we'd put 2 of those together, and then we'd multiply that by 2 v naught over c bar w. Okay, so we're going to be looking at some results here. I just want you to know that this is what's happened. So we, I've solved this set of equations here for the eigenvalues and eigenvectors, but then to get dimensional results out, to look at things in radians per second, for example, or things like that, I've needed to redimensionalize these lambda values that come out, and we'll go through some examples now for that. Okay, so So the particular aircraft that I tested this on, let me just drop in some information about this aircraft. So this is just an example airplane, and so this is actually a glider, an example glider. And so I've called it the baseline glider. This is actually the screenshot of a JSON object that I've used to store all this information that I need in these matrices. Okay, so so you'll see I have a name up here. We've got the wing area, the wing span, which I need. We need the weight, the climb angle, the density, the lift coefficient, the inertia tensor. This is perfectly symmetric, so IXY and IYZ are both 0. This HX, HY, and HZ, those are the angular momentum. That's the angular momentum tensor. So if I had something that is rotating on this aircraft, so for example, a propeller or a jet engine or even a gyroscope that's rotating, that can impart or that influences the forces and moments on the aircraft in a dynamic sense. And so anyway, but I don't on this glider, so it doesn't have any propulsion, so and it doesn't have a gyroscope on board, so those are all 0. And then these three terms tell me what my drag polar looks like, so CD0, CD1, and CD2 as a function of lift coefficient. And then we have derivatives with respect to alpha, derivatives with respect to alpha hat, mu hat, derivatives with respect to beta, derivatives with respect to p bar, q bar, and r bar. Okay, so I got all of these from an aerodynamic code that estimates these derivatives for me. I did by hand need to estimate Cm alpha hat and Cl alpha hat for this glider. Using the methods that I've already described above of how that can be estimated. So, okay, so this is all the information that I need, and now this gives me the information that I plug into this set of equations here. So I'm going to have an A matrix and a B matrix, and then out of that we're going to get the eigenvalues and eigenvectors. So let me switch over to that solution. So this is what that looks like. When I plug those in, this is my A matrix up here, my B matrix right here, and then I actually do B inverse times A to get this into the special eigenproblem, because my eigensolver, I'm using Python. The eigensolver that I use by default just accepts a single matrix, and so so that's the special eigenproblem that I can create by doing B inverse times A. So I call this matrix C, and I plug that into my eigensolver. Okay, so this is the actual matrix that's going into my eigensolver. And then out from that, I get eigenvalues and eigenvectors. So we expected 6 eigenvalues. This is a 6 by 6 system. And so you see I get 2 eigenvalues that are exactly 0. And those are really important. We're going to talk about that in just a minute. And then you can see that I get 2 eigenvalues here that are complex conjugates. So the real parts are identical. The imaginary parts are just are identical but opposite in sign. And then 2 more that are complex conjugates. So I actually get 2 sets of complex conjugate eigenvalues. And then for each of these eigenvalues up here, I have an eigenvector down here and all of the eigenvector information that came out. So I just spit this kind of raw to the screen from this solver, but let's dig into each of these eigenvalues. So I actually have my code then go through and parse out this information and tell me a little bit more about it. So it goes through each of the eigenvalues. So here's the dimensionless eigenvalue. The first one that it pulled out was just a perfect 0, and it has a counterpart that is also perfect 0. So these came out as eigenvalue pairs, and this particular, if you get a 0 for an eigenvalue, that corresponds to what is called a rigid body displacement. Okay, so let me just write that down. This is rigid body displacement mode. Okay, that basically means that there was a parameter in here, one of my independent variables, actually the dynamics of the system don't depend on the actual value for that variable. And so when I look in my eigenvector, so here's my eigenvector here. Now, the eigenvector, these were my 6 independent variables in my system of equations. So let me go back over there real quick. So these are my eigenvector components here, and they came from these 6 independent variables. So the first one's going to correspond to mu, second one to alpha, the next one to q bar, and then my x and z locations and theta, okay? So I've just output those here to the screen because I knew what those 6 were, so I wrote those to the screen, and then these are the corresponding vectors with that. Well, you can see that all of these are 0 except for the one corresponding to my x location. So basically what it's saying is the dynamics of this system are independent of where you choose as your of your x location of the aircraft. And that makes perfect sense, right? It doesn't matter where my aircraft is located or what the x coordinate of my aircraft is. The dynamics should be the same within the approximations that we've made here. So anyway, that's what that's telling us, that the dynamics are independent of this variable here, or of the value of this variable. Okay, and so then the second one, my next dimensionless eigenvalue I got was 0 again. That was the paired with the first one. But this one came out with a 1 with my z location. Now, z location, that may not be quite as intuitive, but again, within the approximations that we've made here, the dynamics don't depend on the altitude of the aircraft. Remember, z tells me the altitude of the aircraft. Now, in reality, it would, because density changes as a function of altitude. But within this linearization, we have not accounted for small deviations in density with changes in altitude. And so because of that, it's saying that our solution is independent of altitude. Okay, so those are the 2 rigid body modes that we're going to get out of these longitudinal equations, the way that we've set it up here. And so anyway, those are the first 2 modes that we get out of this with these first 2 eigenvalues. Now, to back up for just a second, your eigensolver may give these to you in a different order. This is just the order that my solver gave them to me. Put the 2 zeros first. I think that's kind of common, but that's not a given. So you'll need to look at your eigenvalues and pair them with the correct eigenvectors here. Okay. The next eigenvalue that came out, or the next pair of eigenvalues here, this is the dimensionless eigenvalue. It's a complex number, and its counterpart came out here as a complex conjugate. And from this, I can dimensionalize this information here and get a damping rate of 13. So this gives me, that damping rate is hard to know really what that means as a number itself, but from that we can compute the 99% damping time in seconds. So this says that this mode damps out in 0.35 seconds, right? So really quickly. It has a damped natural frequency of about 5, which gives it a period of about 1.3 seconds. So this mode has a period of 1.3 seconds. So if we were to just draw this, so we're gonna, so this is the length of that period, and so 1.3 seconds as it oscillates, but within 0.34 seconds, we saw right here, or 0.35 seconds, is going to be 99% damped out. So that means, although the period is 1.3 seconds, we probably will only experience a very quick return to normal here because the damping is so strong. Okay, so this is a heavily damped mode. So we're really not going to experience one full oscillation of this because the damping is so large. We're only 99% damped out in less than half of a second. Okay, so let's look at what this mode is composed of and what's actually happening in the physics, and we get that from this eigenvector here. So we can look at the components of this eigenvector, and what we're going to be doing here is comparing like values. So for example, our x and z coordinates are like values. the delta mu and delta alpha, those are both non-dimensional velocities. Those are like values. Q is a pitch rate, and theta is an angle, and so that's a little bit. Those don't really have other things to compare to, but we can compare the relative magnitudes of these components of the eigenvector. So let's look at x and z first. So we can see the magnitude of z is large compared to the magnitude of x. Now this has been normalized so that this is the largest component here in this eigenvector, and so it's been multiplied by its complex conjugate so that it is 0. So the imaginary portion of that is 0, and then for each of these eigenvector components, this is the real part, this is the imaginary part, and then we can compute the amplitude and the phase. This is the phase relative to the largest component. So here's the amplitude here, and then the phase of this component relative to itself is 0, but this gives in degrees the phases of these other independent variables relative to a change in this variable, okay? So basically, what we can learn here is that there's going to be a very large change in z and a relatively small change in x. So x is my forward location, and my z is my vertical location. So I'm gonna have a large change in z, but very small change in my forward location from where I would have been at my equilibrium state. Okay, another thing we can see here, but as we compare mu and alpha, remember these two are non-dimensional velocities, is that we're going to have a relatively large change in angle of attack compared to a small change in forward velocity. So this mode is composed, and we can see there's going to be a change in pitch. So we're going to have some pitch rate and some change in theta. Theta seems kind of small, but it's kind of hard to compare to the other components here because it really doesn't have a good counterpart to compare it within this list of independent variables. So okay, so what we understand about this is that there's going to be a large change in z and a large change in alpha, okay? But that it's going to damp out very rapidly. Within a half second, it's going to be gone. Has a period of about 1.25 seconds, okay? This mode is called the short period mode. Okay, and this is an oscillatory interchange between rotational kinetic energy. Let me write this down. Rotational kinetic energy and potential energy. Okay, so if we were to plot this out, what's going to happen is, and actually probably all of you have experienced this if you've ever been on an airliner and hit turbulence. So when you hit turbulence, you feel a very quick bump, but then it dies out. So the aircraft doesn't continue to oscillate from that bump. So it's a quick change. So we'll have a real quick, it looks something like this, really quick oscillatory experience where there's a rapid change in angle of attack. So let me just point this out. Rapid change in angle of attack in z. So remember, our lift is related to angle of attack. So we have a rapid change in angle of attack. We have a rapid change in lift. And that lift then changes our altitude. So in fact, we can see between the relative phases of these. So this here is the phase relative to the largest component here. So about 180 degrees almost, perfectly out of phase almost, is alpha and z. So we're going to quickly change an angle of attack. That's going to pull the aircraft up because it increases the lift. And as we increase, as we climb, because of that change in lift, as the aircraft climbs, that decreases the angle of attack again and drops the lift, and we're gonna pitch up and down relative, as we go through that motion. So anyway, so this is just a really quick pitching motion where the nose of the aircraft will pitch up rapidly, have a quick change in angle of attack. That increase in lift will carry it up, and but as it accelerates upward, the angle of attack decreases and the aircraft pitches back down, and this whole cycle will dampen out very quickly. So this is very common. Like I said, you probably experienced it on the aircraft before. It just feels like a bump because it dampens out so quickly, and usually this mode is not a real problem for aircraft designers. However, we're going to see that this mode is associated with whether or not pilots think an aircraft handles well. So we'll talk about that in a coming video. But the dynamics of this mode, the frequency and the damping of this mode, really drive the opinion of pilots of whether the aircraft handles well. Okay, so so this is called the short period mode, and of course we have so we've got this eigenvalue here, we've got its complex conjugate here. So actually all of the information down in here with this eigenvalue and vector is the same information. We've just got the complex conjugate in this vector relative to this vector, but really no new information. It's got the same damping rate, damping time and frequency and period and things, because these eigenvectors are identical or they're complex conjugates. Okay, so this is the short period mode, and we can see that again this has really high damping, so that's one way to identify this mode. And then the other way is to look at alpha relative to mu. It's a large change in angle of attack and actually a very small change in forward velocity. So we really are not going to change our forward velocity very much, and we're not going to change our x location very much, or forward our translational velocity of the aircraft. Those really aren't going to change much. It's really a change in z and alpha. Okay, so let's scroll down to the next eigenvalue. So this is the next eigenvalue that came out of the system. And again, this is a complex number, and it's got a complex conjugate here as the eigenvalue just below it. So let's go through and see what we can learn about this. So this damping rate is actually much smaller than our previous one. I'll just scroll back up here so we can see that in relative to the short period mode. This is very lightly damped, and it has a 99% damping time of 60 seconds, roughly 60 seconds. Now, this is for this particular aircraft, and actually this glider is a small 9-foot glider. In fact, not even 9 feet. I think it's got a 6-foot wingspan, something like that. So this is a very small glider, and actually on real aircraft, this particular mode can persist for several minutes. This one, it says it can persist for about a minute before it's 99% damped out. But on larger manned aircraft, this can persist for several minutes. The natural frequency, or the damped natural frequency, is 1.2 with a period of 5 seconds. So we are definitely, if we have a period of 5 seconds and this is going to persist for a minute or longer, we are definitely going to see and be able to experience this mode. This will be a real thing that we notice. It won't just be a quick bump that damps out quickly like the short period mode. This mode is called the phugoid. The phugoid mode. Okay, and this is a lightly damped mode. It can persist for a long time, and usually has a period somewhere on the order of 5 to actually can be up to like 30 seconds for manned aircraft. The period can be much longer. So this period is actually relatively short, and that's because what we're looking at here is a glider, really small aircraft. Okay, so let's look at the components of this eigenvector down here and see if we can figure out what's happening. Now, this eigenvector is a little bit different than typical eigenvectors you would get on manned aircraft, and so I'm going to point out some of those differences. Because this is a small glider, some of the relative magnitudes that we get in here are a little bit different than what we would see on a larger aircraft, but it's really not a problem. We can learn a lot here from this. So in this particular case, we've got a large change in x. That's our largest component here, and so you can see that we've multiplied this eigenvector so that this is real. It has a zero imaginary component, and that means that the phase is 0 here. So all of these phases are relative to our change in x. So we're going to have a large change in x, and actually on most most manned aircraft, you'd actually have a similar change in Z. So the relative magnitudes of these would be much closer than they are on this particular aircraft, okay? So again, we can compare the magnitudes here. We can compare mu and alpha. And when we look at these two, you see that alpha is actually 2 orders of magnitude smaller than mu. So this is we're going to see a large change in forward velocity here and a very small change in angle of attack, or W, our normal velocity. So let's plot out what this would look like. So this is our phugoid mode, and it's going to be lightly damped. It's going to persist for quite a while. And actually what happens here is the aircraft actually follows this motion. If we were to look at watch the aircraft in the sky, it would look like it's actually going on a roller coaster ride. So you'd see it kind of follow this motion here, okay? So throughout this motion, there's very small, there really isn't much change in angle of attack because the aircraft is usually or is very closely aligned with the incoming velocity at all times. So we don't have a change in angle of attack, but as it moves up and down here on this roller coaster ride, the aircraft slows down as it climbs and speeds up as it descends, okay? And so that's why there's a large change, or a larger change in our forward velocity here, mu, than there is in angle of attack. Now, X and Z, like I said, usually you would see these closer together in magnitude, so you can see that you'd have a similar change maybe in your Z location as you would in a delta X. Now this X, so you have to remember, this is a deviation in X from where you would be if you had just simply stayed in your steady level flight, or in your equilibrium flight. So you can imagine where you would be if you were just flying forward at a constant speed here compared to the X location as you oscillate here. And so anyway, that's why we have a deviation in both X and Z, okay? Now theta, we're obviously going to be changing our elevation angle as the nose of the aircraft pitches up and down throughout this mode. And Q, we aren't really going to, you see how small Q is here? We're not going to really feel much of a pitch rate. Previously, we felt a much more significant pitch rate as the aircraft pitched through that short period mode. But in the phugoid mode, you really don't feel much of a pitch rate. You feel this roller coaster type ride where the aircraft really isn't pitching rapidly, but it is changing its elevation angle. Okay, so this is a phugoid mode, and this is an interchange between translational kinetic energy and potential energy. Okay, so that's probably a little bit easier to see here. A potential energy is high up here, and then we translate that to, or we gain translational kinetic energy. So we pick up speed, and then the aircraft climbs again. And part of the reason this is happening is because, again, of the lift on the aircraft. So up here, we have a lower speed. We're going to nose down. The aircraft is going to pick up speed. The lift is going to increase on the aircraft. As the lift increases, it lifts us back up, and we trade our kinetic energy that we had down here back for potential energy as we climb up here, and the lift dies a bit. As we lose the lift, then our nose pitches down, and we pick up speed again. So anyway, we go back and forth between this translational kinetic energy and the potential energy. Okay, so this is called the phugoid mode, and like I said, these numbers here may be a little bit low. Both of these here are low for manned aircraft. Usually, this damping, 99% damping time can be on the order of multiple minutes, and the period can be much longer. Now, you may be asking why you haven't ever been in an aircraft and felt like you're on a roller coaster, right? So why haven't you experienced this mode? And that's because the pilot can correct for this very easily. The period here is so slow, and actually the autopilot's going to take care of it most of the time. in airliners and things, the autopilot is handling this. And so we really don't experience this mode very often unless you went up with a pilot in an aircraft and he maybe felt a disturbance or put in an elevator kick or something. There's different ways that you can create a disturbance on the aircraft. And then if he lets go of the stick or if he just freezes the elevator, then and doesn't allow it to move, then you'll see the aircraft go into this type of motion. But pilots, like passengers, don't probably care to go through this, and so most of the time the pilot's going to correct this out very quickly. If the nose starts pitching down and they're picking up speed, they're going to correct out of that and return back to steady level flight. So we really don't experience this in aircraft really at all unless we're trying to experience it. But it's a real mode of the aircraft, and certainly for this glider that I designed here, this glider doesn't have a pilot on board. We don't have any control surfaces moving, and so this will be the natural mode that this glider experiences if it gets any disturbance. Any longitudinal disturbance will excite this mode, and it will begin to play out this mode. The dynamics of this mode will happen on this glider because it's not, there's no pilot correcting it out. Okay, so this is the phugoid mode, and real quick, we also talked about the short period mode. These are the two oscillatory modes that we get in longitudinal dynamics, and they are evident on nearly every aircraft in existence. So they're extremely common, and hopefully at this point you should be able to get some eigenvalues and eigenvectors out of your aircraft. If you put in information about your aircraft and solve these equations, you're going to get eigenvalues and eigenvectors out. And from this information, actually from the eigenvalues alone, you can usually tell which one is the short period and the phugoid simply because of the damping, because this real part is so large compared to the real part of these two. We could have guessed that this was a short period mode because it's a heavily damped mode. But we can go down and look through this eigenvector information in order to better pull out, understand which of these modes is which. So from that we can get our natural frequencies and our damping for each of these modes. And actually in the following videos, we're going to talk about ways to estimate these modes from the original information. So rather than solving this whole system of equations, we can actually estimate what these modes are going to be like just from the information from these derivatives that we were given. There are some closed form solutions out there that are useful for estimating what these modes are without solving this entire eigenproblem. So we'll talk about that in some of the coming videos.